All right, so today I'm going to talk about privacy-preserving dynamic learning of Tor network traffic. This is joint work with my colleague at the U.S. Naval Research Laboratory, Matt Trout, and with Nick Hopper from Minnesota. So we make four main contributions in this work. First, we deploy a privacy-preserving measurement system and use it to safely measure Tor. We then enhance the measurement system to be able to learn Tor traffic models. We use that to build traffic models in private Tor networks, and then we evaluate those models using Shadow. So stepping back a minute, Tor is the most popular deployed anonymous communication system. It has between 2 and 8 million daily users, 6,400 volunteer relays pushing about 125 gigabits per second. So Tor is a very popular system. Recently, services have been adopting the Onion service protocol in Tor. New York Times, Debian, Facebook, and Cloudflare are all using Onion services, which allow them to make their content available through Tor, so you have an end-to-end Torified connection. Tor protects user privacy by separating identification from routing, and this provides unlinkable communication. So a client will build a circuit through Tor choosing 3 relays, establish keys with each of those relays, and then encrypt their communication multiple times. Each relay removes a layer of encryption, and the final relay will send traffic to the destination server. So Tor allows you to protect your privacy and defend yourself against network surveillance and traffic analysis. Tor is also an open research and development platform. All of the code is open source, so you can go on gitweb.torproject.org and look at all of the code. It's also on GitHub. They use open communication systems for their development discussions. They use open IRC channels. They have open mailing lists that anyone can join, and they have open bug and ticket trackers. So as a result of this process, anyone can contribute. You can follow along with the discussion and help the project. This has also inspired a significant body of research. As of a couple days ago, Google Scholar listed over 4,000 citations to the original Tor paper. It's a major research area for many prominent universities, and many master's and doctoral theses, including my own, focus on Tor or a Tor-related research topic. So often, as part of this research, running Tor experiments is useful, but not all experiments can be run on the live network because of user safety and privacy concerns. So researchers have used tools that allow you to run private Tor networks in private environments. And these tools can help you evaluate research design change proposals and trade-offs, can help you attest effects across a range of deployment scenarios and network conditions, and can help you reproduce your research results. So there are a couple of different approaches to this. Shadow is a network simulator that runs a private Tor network on a single machine, and Chutney, NetMirage, and Experiment-Tor do something similar with the network emulation approach. In any approach that you use to create a private Tor network, there's a question of how do you generate traffic in this network. On the live network, on the public network, there are real users going to real websites, so you have this natural traffic. In private networks, we don't have real users, but we still want to have accurate traffic going on in these networks. So how do you do this? Over the last 10 years or so, the sort of unofficial standard has been to represent websites with a single file of a static size. So users in these private networks software in these private networks representing users will just download a file from a server running in the private network. So this single file model, as I call it, fails to capture some important characteristics, such as content length distribution, website structural dependencies like images, JavaScript, CSS files, temporal dynamics, such as those that occur as a part of asynchronous communication protocols, destination diversity, third-party content that's available on other sites, not other than the first-party domain. And all of these things can affect Tor protocol dynamics, like the number of streams that get created and circuits that get created and processed. So one of the main questions we have in this work is how can we generate more accurate traffic flows for use not only in private Tor networks, but also in other research that depends on accurate Tor traffic characteristics. So in this work, again, we make 4 major contributions. We use privcount to safely measure some ground truth Tor statistics. We then enhance privcount and design a mechanism or an approach to learn generative models of Tor traffic. So a packet model and a stream model using hidden Markov modeling and an iterative measurement approach. We then use that to create traffic generation tools that can create traffic in private Tor networks. And we evaluate our new models against previously used models. So first, I'll talk about Tor measurement. So we're going to use the privcount measurement system to measure Tor. Privcount is a privacy-preserving counting system. This was designed to safely collect useful Tor statistics. This was originally published at CCS in 2016 and is based on the PrivX secret sharing protocol, which was published in CCS 2014. Privcount security goals include forward privacy, so an adversary cannot learn the state of measurement before the time of compromise. Secure aggregation across all measurement nodes. So this means that if you have a number of measurement nodes, you learn the combined aggregate of a specific statistic without learning individual inputs from the nodes. And the measurement results are differentially private to protect user actions by adding noise to the statistics, more or less. So privcount itself is a distributed system. You have data collectors that generally run on relay machines, collecting events from the relays and counting things. And then you have a tally server and some share keepers that are part of the secure aggregation process. So we deployed privcount on a set of 17 relays, including 11 entry relays and 6 exit relays. Every relay we ran, we connected to a privcount data collector, and then we ran 3 share keepers and a tally server as part of the privcount protocol. Using this deployment, we collected various measurements of the Tor network. I'm not going to get into the details of all of these. Please see the paper. We have lots of statistics, but we measured things about clients, how many circuits there are getting created in the network, how many circuits there are per client, total numbers of circuits and streams, total numbers of bytes being sent, streams per circuit, bytes per stream, etc. I will give you one example of something we measured, and this is the number of circuits per client. So this graph shows, on the x-axis, shows the bin that when a circuit closes, when a client leaves every 10 minutes, we count how many circuits did that client create. And then we increment 1 for every client, depending on which bin it fits into. We measured this for active and inactive circuits. Inactive circuits are circuits that are built but not ever used to actually transfer any traffic, and active circuits are actually used for traffic. So this gives us a histogram like the one shown. We find that many of the active circuits clients are using 1 circuit only. This could potentially be clients that are going to a single website or perhaps not really browsing around much. We also found there's quite a wide range, up to 15 or more circuits. Some clients are creating up to 15 or more circuits and 15 or more inactive circuits. We believe this is due to Tor's preemptive circuit building. So when you start Tor browser or a Tor process fresh, it will create a number of preemptive circuits in order to use them later if you need it. And if you don't use them, they would count as inactive circuits. So again, we collected a variety of measurements. There are more results in the paper, so please see that if you're interested. Okay, so next I'll talk about how we learn Tor traffic. So we're going to use hidden Markov modeling and exit relay observations along with privcount to safely learn models of streams and packets based on live Tor traffic. So our privcount system and the relays we're running, we will be taking these observations from exit relays. And exit relays can observe traffic exiting the Tor network going to servers on the internet. This means exits can observe when a circuit opens, the number of streams created on that circuit, and when the circuit closes. And this will be used for a stream model. It can observe when a stream opens, when packets are going in both directions to and from the server, and when the stream closes. And then for both models, we use inter-event timing. So hidden Markov models are generally a way for us to model an application process. So here's an example of one for our stream model. We have 4 states. Circuit opens in the starting state, and then we have 2 states for circuit creation. One is active, where circuits are created more rapidly, and one is a dwell state, where circuits are created less rapidly, and when the circuit closes in the end state. So the green arrows represent state-to-state transitions, and the blue arrows represent state-to-observation emissions. So in certain states, you can actually emit an event. And all of these edges have probabilities associated with them. And on the emission edges, we can model different distributions of delay times. So how rapidly do we want to create streams? So we have this hidden Markov model structure, but we can't just learn this. We can't just produce a hidden Markov model based on Tor traffic. We actually start with an HMM that we train based on internet traffic. So AS2500 is a research ISP in Japan that collects information, basically trace route on its ISP, and makes this available as part of a research project. So we use this TCP dump and we extract TCP flows from it, and then we can train based on those. We cluster the flows and train an initial HMM that represents something what internet traffic looks like in that AS. And then our process is to take that initial internet-based HMM and put it into our priv count process. And then as we observe Tor traffic on circuits, we will take our sequence of streams or sequence of packets and run the Viterbi algorithm to find the most likely path through our HMM. And then for every edge that was traversed as part of the most likely path, we increment a priv count counter. And then, so following the measurement, we can update the probabilities on each of the edges and then weight the previous HMM probabilities with the new probabilities that we compute based on our priv count measurements. And so we can do this iteratively over time. And actually we measure for 1 day each. So we take the initial internet HMM, measure for a day. This outputs a new perturbed HMM that should be closer to Tor, representative of Tor traffic. And we do this 14 times in a row. So we have an initial model and 14 Tor models. And so we then evaluated how we're doing with these models. Are we getting better, closer to Tor traffic, or not? And so this graph is a heat map that shows for each of the models that we're measuring on the x-axis, the fraction of observed sequences that are more likely under model X than under model Y. So if over these sequence of stream models, we continuously get better and better, you would see the bottom right of the diagonal, the part of the graph would be completely yellow. And it turns out that we do improve, we see that our models improve up until about stream model 9. And then it starts to get a little bit cold again, darker, meaning that our models after model 9 are a little bit less, not well as representative as model 9 of Tor traffic. We think this is because of short-term variability in Tor traffic, but more work needs to be done to verify this. So we did this for a stream model and also for a packet model. I was just giving the stream model as an example here. Obviously, more details will be in the paper. Okay, so the last part is evaluation. We built a traffic generator called tgen, which is based on an action dependency graph that allows us to configure in software how we want to create TCP connections and how we want to transfer traffic on those TCP connections. And then we created several tgen model configurations to represent the different traffic models that we want to test. And we created a tgen config for the single file traffic model. And then we created one for the priv count model based on our measurements, including our HMM models. And we also created one for a separate model, a protocol model, which is based on protocols that are guessed to be popular on the Tor network. And we have some evidence for this. So we did one based on HTTP using HTTP archive data set, which provides information about websites on the internet. And we downloaded several torrent files and used that to create a BitTorrent model. So we then evaluated these different models by running them in a private Tor network created using Shadow. Before doing our Shadow experiments, we realized that the existing Shadow topology, so the latency between the nodes in Shadow, was 5 years old. And so we went ahead and updated this using ripe atlas probes, which are located all around the world, as this map, as the map shows. We did about 5 million pings between representative probes, one per city. So this gave us 1,813 cities, and we did multiple pings between each pairs of cities to get an estimate for latency. And we use this map in our experiments. We then ran each of our 3 tgen configurations in Shadow. When doing this, we used the same Tor version that we ran on the live Tor network, which is capable of exporting the priv count events that we need for counting the ground truth statistics in Tor. When running this in Shadow, we configured our relays to export these priv count events to files, and we save them to disk. And then following our Shadow experiments, for each of the relays running in Shadow, we loaded these priv count event files into a local instance of priv count. And then this outputs the same statistics that we measured in the live Tor network. So this is a way to easily compare our results. So this graph shows a comparison of our different models. To compare these, we looked at the statistics. The x-axis here shows a variety of statistics that we measured in the live Tor network, and the y-axis shows the distance, which is the Earth mover's distance, which we used as a metric for closeness. As you can see, across all of the statistics, the single statistics that we measured, the priv count model is actually closest. Ideally, we would be 0. 0 would mean the same as ground truth. So the priv count model is the closest to 0 across all of these statistics. And actually, we see that the protocol model does a little bit worse, primarily because it's creating 340-something% of the streams that it should be creating. Cumulatively, across all of these statistics, the single file model was 700% roughly from ground truth. The protocol model was 1,000%, and priv count was 400%. So to summarize, we safely measured Tor. We enhanced priv count to be able to learn Tor traffic models using hidden Markov modeling. We built traffic models and ran them in private Tor networks to evaluate the difference between these and other approaches. All of the code that we wrote for this has been merged into priv count and Shadow, open source projects, and the data, the code, and more details are available at this website, the GitHub website that I created. So please check it out if you're interested. As extensions in future work, we would like to explore measuring traffic models over longer timescales to see how this affects the variability in relay traffic that we observed. We're also interested in creating and measuring a circuit creation model. We didn't do that in this paper. And I'd like to further understand the effect of traffic fidelity on actual research results. Does it actually change the result of research by having more accurate traffic? And with that, my contact information is here, and I'd be happy to take questions.
Hey, thanks. Sorry. So you said you trained the model initially on the AS2500 data, but that data won't have any notion of circuits, but you're training a model that has to do with circuit creation and destruction.
So we didn't. So you're right. The data doesn't have circuits in it. But we didn't train a circuit model. We trained a stream model and a packet model. So this has TCP flows, and it has a variety of TCP flows from the same client. So that represents creations on a circuit, right?
So you used you use client IP as a stand-in for circuit.
I believe so, yes.
Okay, great.
So I didn't see anything on jitter or latency variation in your papers. Did you think about that, or are you using just what's currently in the shadow model from before?
So you're talking about in the model that we enhanced with the new latency measurements. Yeah, we did. I think we might have some statistics about that. They're not in the paper because it wasn't central to what we were doing, but we launched at least 3 latency probes between each pair of cities. And I believe we took a measurement as long as we got 1 successful result between 2 cities. So sometimes they don't respond. So we threw those out. And yeah, I don't know. I don't have any information about jitter or variability between a pair of cities. Part of the issue was this required a lot of credits. Atlas works on a credit system. And so you need to run probes or get credits from someone in order to run these measurements. You need to contribute an Atlas probe to the system, which earns you credits.
Sure, but just so stepping back, I mean, Shadow must have some kind of model for jitter in it. That has not changed, I guess. Is that the...
Shadow does have the ability to specify jitter, but it's not used.
Oh, okay.
Generally. It could be used.
One quick question. You use priv count for privacy, like noising your data, right? And you inherit one challenge from priv count. If you take subsequent sessions from one person and have subsequent sessions of another person, the longer the chain of sessions is that's subsequent, the more the sensitivity diverges. So the more noise you would need to hide these 2 sequences of sessions, to merge these 2 sequences of sessions. If I remember correctly, priv count doesn't learn something like a machine for one user and a machine for another user, right? You just add noise to one session. Is that correct?
We add noise once per day. We add enough noise to cover a set amount of actions for that day.
Okay. I have the feeling, we can take it offline. I have the feeling that the sensitivity is far larger than you probably estimate in your analysis. But then
it might be true, yes. Not.
Okay. Let's thank the speaker again.